Okay, so it's 5 o'clock. Hello, everybody, to the KNIME Extended Online Summit. My name is Christian Dietz. I'm with KNIME, and I'm here today with Gopi, who is a PhD student at the Queen's University, and he will be talking about automatically detecting data science pitfalls in KNIME using KNIME. Okay, and before he explains to us what this actually means and how he detects those data science pitfalls with KNIME in KNIME, I was asked to give some instructions. So first about the Q&A section. So at the bottom of Zoom, you find this Q&A button, and there you can send us questions. And make sure you send us the questions and also you upvote your own questions, such that we can actually answer them at the end of the talk. Also, if during Gopi's talk, you actually can't see the slides, but only Gopi, which is nice, but maybe you also want to see the slides, then you can switch to gallery view in Zoom and then make sure you see the slides. All of the talk will be recorded and made available to you with the slides by tomorrow. And with having all of that said, I'm really happy to listen to your talk, Gopi, and the stage is yours.
Thank you, Christian. Let me just quickly share the screen first. I'm hoping you guys can see the screen at this point. So, greetings everyone. Greetings to everyone around the world. I'm Gopi. I'll be giving a talk on automatically detecting data science pitfalls using KNIME, in KNIME using KNIME. So before I start the talk, I hope all of you guys are safe and well. I know these are testing times, and I hope you guys stay safe. So this work was done in collaboration with Gustavo, Ahmed, and Dingle, and Professor Jürgen Dingle, and we all work in Queen's University. So I myself am a PhD student working under the supervision of Professor Hassan. So I will start talking about the actual stuff. So I'm assuming all of you guys are ardent users of KNIME. So there are some nice advantages to data science pipeline tools like KNIME, right? For instance, it's abstracted. So you're always hidden away from all the complexities of the data science process, which, as we all know, can be quite complex. And it also enables like super easy automation for us. So with advantages like these, it's almost a no-brainer not to use this anymore. But and it comes around with documentation, and it enables you to do the whole thing really fast. So why am I here? What am I giving you a talk about? So this is the problem. So all of this is made so easy in tools like KNIME. For instance, if you want to build a whole data science pipeline to derive some insights, you could probably do that in 2 minutes in a tool like KNIME. But all this easy access enables like super easy mistakes. For instance, one of the studies by Krishnan and Mendes in a Promise conference shows that when the linear regression, which is the simplest of the algorithms, also quite complex, depends on who you ask, but which is one of the simplest of the algorithms, when not used correctly, can provide insights that are terribly wrong. And similarly, one of the more recent studies show that because there are so many automation tools available these days, and there are many people who do not fully understand these tools, use these tools, they make a lot of mistakes, which in turn results in failures of analytics projects. So to avoid all this, the goal of what we did here was to enable an easy way that is still in the spirit of automation, abstraction, and everything, and allows practitioners to trivially start detecting the common problems in their data science pipelines that they built. So what we did to do that was we developed this component called Pitfalls Analyzer, which is a wrap metanode in KNIME. And so if you drag and drop this component to any of your any of the data science pipelines that you built, it tries to flag for all the potential pitfalls, pitfalls in your data science pipeline. So this works more or less like a static analysis tool, but in the context of a data science pipeline. So I'm hoping all of you guys have seen the movie Despicable Me. So Minions, they're my favorite. They're one of my favorite cartoon animated movies. So I'm going to try and explain how this pitfalls analyzer helps Minion exactly understand how to make a banana plant grow. So for people who do not know, Minions love bananas. So there's a Minion. It tries to see, okay, it wants to understand what makes the banana plants grow. So the first thing it does is it collects data like any good data scientist. Goes ahead, it collects all the data, makes the independent features, and then builds a pipeline using one of these tools. I'm assuming Minion does not have too much expertise to code things up, so it's going to use some things that some data science pipeline tools like KNIME that help it build a pipeline quickly. And then it finds that, okay, so manure is the most important factor to make sure the bananas grows fast and everything. So it goes ahead and orders a ton of manure from online, say Amazon. And then it just changes the data order, or it sees that, just to see what happens if it shuffles the data. And it just reruns the pipeline again. And it finds that suddenly weather is the most important factor. And this is not good, right? Like the Minion just ordered a bunch of manure. So what happened here was that our Minion failed to remove the correlated variables from the data set. So if the correlated variables are present in the data set, depending on the order in which the data is fed into the machine learning model, the insights that the model generate might vary. So this is one of the very common data science pitfalls that any practitioner needs to be aware of. So just as a quick aside, so for people who are not familiar with Nicolas Cage is an actor who has acted in some really good movies and some really terrible movies. So what is correlation? Correlation is just two variables varying together, and the presence of these variables in the data analysis pipeline leads to muddling of insights, in the sense that one of these variables can show up as more important, where in reality the other thing would be the most important one. So for instance, consider your data set has these two data points, something about the times when Nicolas Cage movie was released and the number of deaths. Now, a number of films that Nicolas Cage released in a given year, and number of deaths that happened by drowning in a swimming pool. And if you're trying to build a model and you have these two variables in it, it might probably even show, Nicolas Cage is one of the most important variables in predicting death by drowning. And we don't want spurious correlations like that, right? On a more serious, and so I try to make a jest out of it, but on a more serious note, there are data analytics and data science is being used in analyzing data, things like pacemaker and flu trends and things like that. In situations like a pandemic, right? Like you're trying to understand what is the most important feature that spreads the virus and things like that. And in that case, if there are correlated variables present in your data set, you might start thinking one thing is more important, whereas in reality, a hidden confounder or another variable is the one that's most important. So we need to be cognizant of potential pitfalls like these, and we need to handle them. So what our pitfalls analyzer does is, once this pipeline is generated, and we drag and drop the pitfalls analyzer component, it analyzes the pipeline and identifies for the common pitfalls, and it immediately flags something like saying, so you do not have a correlation filter, so please be careful when you're interpreting your features. So a warning like this would go a long way in helping the data science practitioners to quickly realize, oh yeah, I forgot to deal with correlation, or in this case, I'm only worried about the performance of the model, so I'm not going to worry about correlation. So the decision might lie with the practitioner, but they will be it would be informed decisions from now on. So we cannot. So right now at this point, because it's a prototype, we do not support all the common data science pitfalls, but we do support the pitfalls that are identified by Tajitam, Taman, and Hassan in one of these studies that they published in 2018. So these are the pitfalls that our pitfalls analyzer component currently identifies in any KNIME data science pipeline. So first, absence of control variables. So control variables are those variables which needs to be present in an analysis. Like for instance, take a medical trail. So you need to always see if a new drug does better than already existing state of the art. So otherwise, if we just give the new drug to a group and we find that working as a treatment, we wouldn't know if it is any better than what is already existing. So an analysis should always have control variables present in it. So if the control variables are absent, our pitfalls analyzer will identify those control variables, the absence of those control variables. Second, not accounting for correlated variables, which we just went over in detail. And third is not accounting for the impact of data rebalancing techniques. So you might ask, what is the problem with the data with using data rebalancing techniques? But many recent studies suggest that when you're trying to derive insights out of the data, not just trying to build a model that performs the best, data rebalancing techniques can actually induce concept drifts. So the interpretation or the insights that you generate out of this pipeline might be negatively impacted, or it might start giving you spurious results. And so this is another interesting pitfall. So for many of us, or at least for me, like 4 years ago, maybe, if I build a pipeline with a machine learning model in it and it provides me an accuracy or AUC of more than 80, I usually get a very warm feeling that I've done something right and it's all going great. But many recent studies actually show that when the hyperparameters of a learner are not tuned, the results that you get cannot be taken at face value. The learners could be improved a lot more, and it also and recent studies also show that the insights that you generate from the learners or the machine learning models vary tremendously once you hyperparameter tune. So it's pivotal that every data science pipeline hyperparameter tunes the algorithms that it uses. So similarly, another pitfall is to use threshold dependent metrics always. So while accuracy is great, we all know that accuracy is easily influenced by class imbalance problem. And similarly, many threshold metrics like precision, recall have problems that are inherent to it. So it's nice if we want the data science practitioners that you're only computing all your performance on threshold dependent metrics and you lack non-threshold dependent metrics like AUC here. So that is one of the pitfalls. And another pitfall is, so this is again a very famous one, right? So I think we did a survey once, and almost 80% of the studies in the last 3 years in both machine learning and data mining conferences only use tenfold validation. And with my years of working in industry too, tenfold validation seems to be the de facto. But both in statistics and software analytics, there are many studies that show that cross-validation is not the most unbiased method of seeing if the performance generalizes well. In many cases, Bootstrap and other metrics, other validation metrics are superior. So flagging when only cross-validation is used is also could be useful for the practitioners. And similarly, ANOVA type 1, when it's used to interpret the models, to generate the insights from the model, to see which feature affects the model the most, and things like that. It's problematic because, once again, ANOVA is very sensitive to the ordering of the independent features in the data. So it's always better to use ANOVA type 2 actually, or type 3, depending on your assumptions. But ANOVA type 1 is extremely prone to misleading results. And then finally, interpreting the coefficient of the regression model directly. So once again, a plethora of research shows that interpreting the coefficients of a regression model is not the right way to derive insights out of a regression model. So these are the 8 pitfalls that we set out to analyze. So the nice thing about our approach so far is that we provide an approach that is implemented in KNIME and it is available as a meta node in KNIME, but it is also just an approach which can generalize well. So before I go into how the approach works or how we detect these pitfalls, just to make sure that they're all using the same terminology, I call this a node, I call this an edge, and I call the whole connection a directed acyclic graph. A directed acyclic graph is something that does not cycle back and charts the data and execution flow in a KNIME pipeline. So how does our pitfalls analyzer work? So you start KNIME, you create a pipeline, you add a component. That's all. So a little more insight into how the actual approach works. So if you don't end up understanding my abstract presentation of the approach, please don't despair. I have examples with the actual pipeline, so it would be more understandable as we go on. So as we have the pipeline, so we detect the pitfalls in our pipeline in the following fashion. First, we take the pipeline, we extract the DAG of the pipeline, all the independent DAGs of the pipeline, which is all the independent directed acyclic graphs of the pipeline. And once we extract these, we first see if these DAGs have a machine learning model as a part of them. If a machine learning model is not present as a part of this execution graph, then there could not be any pitfalls, because all the insights that we generate and the pitfalls that are associated with it are because of the presence of a machine learning model. So once we verify that the machine learning model is present, we extract the execution subgraph of each learner. What do I mean by this? So whatever data and control flow that comes in and goes out of the machine learning model is charted as a single directed acyclic graph. So once again, if this is not clear, it would be clear as we go on. And then once we have these execution subgraph, we check for a relevant anti-pattern. So anti-pattern is what makes up a pitfall. So for instance, right, like if you want to, if you do not remove correlated variables in your analysis, you will find that by seeing that there is no correlation filter present in the pipeline. Similarly, for other pitfalls, there are specific anti-patterns that appear. So we search for a relevant anti-pattern in the execution subgraph of the learner. And then if the relevant anti-patterns are present, we report them. If not, we say there is no pitfalls. So some of the example anti-patterns are, so to find pitfall 2, which was about correlated variables, we check if a correlation filter is present in the backward subgraph of a learner, which means that before the data is fed into the learner, the data should have gone through a correlation filter. And similarly, to see if the threshold independent metrics are being present, it should be ROC curve or some other threshold independent metric node must be present in the backward slice of the algorithm. Sorry, I misspoke. The correlation filter should be present in the forward slice, whereas the ROC curve should be present in the backward slice. Whereas for a cross-validation, both the beginning and the end of cross-validation nodes should be present in both the forward and the backward slice, because the process starts and it loops over the machine learning model. So let's focus on how to identify the correlated pitfall by considering this example. So this is a quick example pipeline which I built for some of the one of the data analytics purpose, and it has 3 learners in it, and we want to see if these learners suffer from the pitfall number 2. So for the purposes of this presentation, let me focus on the decision tree learner node. So when you drag and drop the pitfalls analyzer component, it does the analysis for each of the learner. So it'll give you the pitfalls present for each of the learner that you've used in your model, used in your pipeline. So in this case, as you can see, the data comes from the file reader, and it goes through the binner partitioning and normalizer only for the random forest. But for the decision tree, it goes through the normalizer and then comes straight to the partitioner. So which we see through this graph. So this forms the pipeline that comprises. This forms the pipeline path that only comprises the decision tree. So from observing this, we could see that it exhibits correlation pitfall, right? Because there is no correlation filter that removes the correlated variables. So what we first do is we check the forward slice, which is only the slice that is before. So this presents the, sorry, I keep confusing the backward slice and forward slice. So this is the backward slice, and anything that leads from the learner is the forward slice. So the backward, we only extract the backward slice because we check for a correlation filter in the presence of a correlation filter in the backward slice, and we see that there is no correlation filter that is present in the backward slice. So once we find that, we flag that and we report it to the practitioner. So this gives you an idea of how we implemented our pitfalls analyzer in KNIME. So each component that detects the pitfall, individual pitfall, was a wrapped metanode. And for the control variables alone, we need to pre-specify what the control variables are for this expected analysis. So at every time when the data set is fed, it will automatically check. So the correlation filter, so the correlation pitfall is detected with this component that I've highlighted. And once we expand that, as I told you before, we first extract the names of all the individual nodes that we use, and then we check for the presence of a learner. And once we check for the presence of a learner, we see if the anti-patterns are present. And once we establish that the learner is present and the anti-patterns are present, we see if the anti-patterns are present in the execution subgraph of the learner, that is, in the path of the learner. For instance, as we know, a pipeline can contain multiple learners, right? So some learners, even though the anti-pattern nodes might be present in the pipeline at large, it may not be a part of the execution subgraph of one of the learners. So for that given learner, it might not have those problems. So that is why it checks if the anti-pattern nodes are present in the exact execution subgraph. So once we did this, we also analyzed this by testing our component on some of the pipelines that were available and created by KNIME, actually, for the problem of electricity consumption prediction in Ireland, and rotor failure detection of a windmill farm, and a bike share predictive analytics. So they had 7 pipelines for the first case, and 3 pipelines and 1 pipeline for the other case. And this is a summary statistic of all the number of nodes and the number of pipelines in each of the project. And we 2 of the authors manually went through this whole pipeline, all of the pipelines actually, to see what are the pitfalls that are present. So I present the pitfalls that were present here. And it took us almost an hour to go through all of this and identify this. And when we did the same thing with our pitfalls analyzer, it analyzed all the pipelines in a matter of mere seconds. So so I assert that our pitfalls analyzer is both scalable and really efficient. So in summary, right, KNIME and tools like KNIME make the world an easier place to live in. However, making it as easy as possible, we also invite easy mistakes to creep in, which I explained with how Minion R is a banana and how it might go wrong if it doesn't treat one of the pitfalls. And we also saw how what the pitfalls that our component is capable of handling at this point. And I demonstrated that our pitfalls analyzer is efficient and automates the whole thing and makes it scalable. So that was my talk. I'd be happy to answer questions now. And if you're interested in this research, I really suggest you to read the paper. This was published in Models, and that might have some of the details that I glossed over due to the time. Or you can always send me an email, and I'd be more than happy to answer any questions with regards to implementation or the subject matter. Thank you. Thank you for listening.